Before going to halfwave rectifier using MATLAB Simulink, if you know about halfwave rectifier theoretical view, then you can easily design the halfwave rectifier in MATLAB Simulink. Okay, if you don't know about halfwave rectifier, just I will give the video link in description. Just watch it and then again come to this video and you can easily design the halfwave rectifier. Let's see how halfwave rectifier connected in MATLAB. So this is the circuit diagram of halfwave rectifier. Here you have the input source as this is AC, right? Actually halfwave rectifier means it converts AC to DC. So input is AC, right? This is the AC input, right? So this AC input is connected to diode. This is diode, right? And then connected to the load resistance. That's it. So here you need only three elements like input AC source and diode resistor. That's it. If you have these three elements, then you can easily connect. Now open your MATLAB and go to Simulink. Here you can connect the circuit. Okay, in Simulink go to blank model. So this is the place where we connect the circuit. Okay, now what we need? We need just three elements, that is AC input source, diode and resistance load R. So take these three from where? From library. So this is the library. Go to library and go to Simscape and go to power systems, specialized technologies. Then you can get the circuits. Here we have AC source, right? This is the AC source, nothing but the source. So in sources you will get the AC source. So go to sources and take the AC voltage source. You can directly add blank to new model, or you can also use the shortcut Control I. Okay, and next what you want? We need a diode, right? This is the diode, right? So we need a diode. So in diode, where we get diode? In power electronics we get the diode. Go to power electronics. Here we have the diode. So and then what we need? We need a resistance load. Okay, so go to elements and take RLC branch. See this RLC branch. Here we can get the only combination, not separate. Okay, then after we can filter. Okay, that's it. So here if you need to see the input waveform like this and output waveform like this, you need a voltage measurement. Okay, this is the voltage, right? So that's why we need a voltage measurement to measure the voltage of input and output. So go to measurements, then take voltage measurement also. To see the waveform like this, we need a scope, right? In scope we can able to see the waveforms. Go to sinks, then you can get the scope to see the waveform. That's it. These are the elements what we need. Okay, so take and each and everything. So now connect the circuit as per our circuit. So take AC source and connect this to the diode like this. That is our circuit. And if you want to rotate this one, just use the shortcut Control R to rotate. That's it. But actually this is the combination of three, right? But we just need simple R road, right? So take R only. And that's it. Give it to the cathode and give it to the source. To measure the output voltage, take the voltage measurement as parallel to load, like what we done in labs. Also we can connect the voltmeter in parallel, right? And we can connect the ammeter in series like this. To connect the voltage measurement, just take the parallel connection. Okay, that's it. Like we can get the output voltage, and if you want to measure the input voltage, take another voltage measurement as right click on this, then you can easily copy, connect positive and connect negative to the negative. To measure the input voltage, take on the scope by right clicking that one. If you want to see these two waveforms as one waveform, just take another scope and edit these one as two inputs, right? We have the two waveforms in one scope, so that's why I'm taking two inputs. Then you can easily get the two inputs here. So I want to see this one input, I want to see output in one scope. So this is the connection to see the two graphs in one. So here if you double click on each and every element, you can get the values. Okay, to double click on voltage source, here we are giving the 100 volts AC. Okay, this is the peak amplitude and we are taking the frequency rate, 60 frequency I am taking. That's it. Okay, and this is the diode and this is the resistance I am taking, 1 ohm resistance. That's it. So actually this is the time period of our graph. Okay, now so this is nothing but the x-axis. I am taking just 0.5 x-axis, nothing but the time period. 0.5 I am taking. Okay, this is the time period, nothing but the x-axis. Okay, now run your circuit. If you run your circuit, you can get the error, that is you need to connect the power GUI block. Okay, actually that is a library file. Okay, so take power GUI also. Without that one we can't run any circuit in power electronics. So in fundamental blocks you can get the power GUI. GUI means what? Graphical user interface. Okay now, so what is power GUI? It is called a graphical user interface. Without this one we can't run the our circuit. Okay, this is act as a library file. Okay, go to here we have the three simulation modes. One is continuous, discrete, phasor. Our circuit is discrete form, right? To take the discrete only and click on OK. That's it. That is the use of power GUI. Without this one we can't run the our circuit. That is a library block. Here power GUI means power graphical user interface. That is the interface between graphics and users. That's it. Okay, now you can easily run your circuit. You don't get any errors. So now if you want to see the input, click on this is the input voltage measurement, right? So in scope 1 you can see the input graph. So this is the input what we are giving, 100 volts AC, right? 100 volts peak, 100 volts negative, 100 volts positive, 100 volts negative. So this is the AC, right? 100 volts AC, that is the what we are giving here, right? So I am giving 100 volts and I am getting the 100 volts in input. Okay, so what about output? So if you see the output measurement, right? So in scope you can get the output voltage. So this is our output voltage. That's it. Here you can be able to see only positive peaks, 100 and 0, 100 and 0, 100 and 0. So this is called half wave, right? In full wave what we have input in positive and negative also. We have positive and negative 100, positive and negative 100. But here you can go get to only half wave. That's it. Okay, you can get the clarity clearly in scope 2. Okay, this is the scope 2 means you can take the input and output as one scope. If you double click this one, so that yellow color shows the input and blue color shows the output. Okay, in input you can get the positive and negative 100, right? Yellow color shows. But output what we get only half wave. So this is the half wave, only positive peaks we get. That's it, right? Only positive, only positive, only positive. That blue color indicates positive waveform. Okay, nothing but the output. So that's why it is named as a half wave rectifier. If you give a full wave, we're getting only half wave. Okay, but this is not a full DC, right? Actually rectifier means what is rectifier? Rectifier means it can convert AC to DC, but in this circuit I am giving the AC but I am getting the only half wave, positive and 0, positive and 0. Actually DC means straight line, right? This is straight line DC, right? But we can't get this one. Okay, you need to get at least near to DC, right? But it is 0 value, but DC does not have 0. Okay, it has only positive value of DC. That's it. So that's why I am connecting the capacitor parallel to the load. That is nothing but the smoothing capacitor. What will happen in smoothing capacitor operating in continuous conduction mode? I am getting the charge discharge, charge discharge, charge discharge, like this waveform. Okay, so that's why I am connecting the capacitor to don't allow the voltage to 0. Okay, I am not allowing the load to 0 voltage. So I am getting the near to DC, right? That's why I am using the smoothing capacitor. So take smoothing capacitor here. Smoothing capacitor, nothing but the capacitor. Just right click and drag this one. Okay, double click and then take only capacitor. That's it. Okay, connect in parallel. This is the passive filter. Okay, so take any value 0. For example, I am taking 0.03. Okay, I am taking 0.03 farad. Okay, now run your circuit. What you will get? Okay, you are accepting the 0. Actually it does not go to the 0, right? It does not go to the 0, but here also you are getting the huge difference. It is not a pure DC and it does not nearer to DC. So if you want to get nearer to DC waveform, you need to increase the capacitor value here. So here I am taking 0.003, right? So I am increasing little bit. So I am taking only 0.03. Let's see what we get. So here, yes, it is like nearer to DC. Okay, 0, if you see 0 is here but our DC is here. So if you see this one, this straight line is DC, it's nearer to this one, right? If you further increase the capacitor, what will happen? Further increase the capacitance, just take 0.3, that's it. and enter and run it again. What you are getting? Yes, this is much nearer to DC, right? That is the use of capacitor, smoothing capacitor. Without this capacitor we can't get the voltage nearer to DC. That's it. That is depending on this value only. Okay, so that is the use of smoothing capacitor. If you see that both waveforms in one waveform, go to scope 2 and click that blue one indicates output. That is what charge discharge, charge discharge, charge discharge, and this yellow line indicate input. I am taking the 100 volts positive and 100 voltage negative. In output voltage you are getting the 100 volts nearer to 100 volts, like this is the nearer to DC. That's it. That is the use of smoothing capacitor. So this is how we learn the half wave rectifier using MATLAB.